everyone. In this video, we're going to talk about work and the PV diagram of a cycle. And this video is part of a short video series on internal combustion engines. So we're going to get started. We're going to talk about how work affects our engine and how we can extract the work from our engine. So if you haven't caught up, please watch the videos before these in the playlist. If not, if you're just looking for general information on work, here's what we're going to talk about. So work is actually the measurement of output of an engine. And typically we talk about power. Work is just related to power in the sense that power is the rate of work, or power is essentially work divided by time. So if we go to our understanding of work, essentially, if our piston is moving up and down, it is either creating positive work or using negative work. So usually we assume that work is positive going down. Now, if you'll remember from other engineering classes that you've taken potentially, or by some reading, you'll know that work is equal to force times the distance. So if you put a force on a piston and the piston moves a certain distance, you essentially have some work. And what we can say is that in an internal combustion engine, the gas pressure, okay, so that is not the gasoline pressure necessarily, but the actual vapor pressure or the gas pressure actually generates some work. So the reason why our piston moves down is because we have a combustion that is happening in the top of our engine and essentially is creating some pressure down. So there's some pressure onto the piston, and then the piston starts moving. And we can kind of write the equation of work as work is equal to force times distance. However, this equation just equates for the fact that essentially work would be the average force times the distance covered. So the force doesn't necessarily have to be linear. Whenever the force isn't linear, your work is actually written as follows. It's written as the integral of f dx, where dx is your movement into the axis, for example. So your x would move along this direction, and so we have the integral of f dx. So that means that if the force is variable, we can integrate the force through the whole distance that it covers, and we will find the total work. Now, typically in an internal combustion engine, the work is not constant, so we do have to use that form of the equation. But we're going to see throughout these videos that it actually gets simplified a little bit as we go forward. So work is equal to the integral of f dx, and we can then write that since force is equal to pressure times area, we can actually use the gas pressure to figure out what the work would be. And so we can write that work is equal to P times the area of the piston, or A sub P times dx. And we can recognize as well that this part of the equation is actually, so the area of the piston multiplied by dx is actually the change in volume, or dV. So we can finally write that our work is equal to the integral of P dV. So if we know our change in volume in our engine, and we know our pressure at every point in time in the engine, or every point on the distance of that the piston covers, essentially we can find the work. And so what we can do is we can actually plot this pressure times the volume on a diagram. So we can look at a diagram and look at the pressure times the volume position of the engine, and we can figure out what that we can actually figure out from that diagram what the work is, and we'll talk about how we do that. So looking at this diagram, I've copied over a diagram that illustrates this pressure times volume for an internal combustion engine, and we can see that we have pressure versus specific volume. Now, at the bottom here, we could substitute specific volume with regular volume, which is capital V. Okay, so we have a lowercase v for specific volume, a capital V for regular volume, okay, or total volume. So in order to convert between the two, what specific volume means is just that volume is equal to mass times the specific volume. So it's divided by the mass. But typically we use either volume or specific volume. It's kind of the same thing. So I'm going to erase this just so that we can write something under here that's going to be of importance. So if we look at this diagram here, the first thing we can do is we can kind of map our piston under the diagram itself. So we have the diagram here, and what we can do is we can actually draw a sideways piston to kind of model what's actually happening here. So we can model a sideways piston, a sideways cylinder with a piston inside it. And the piston, for example, at top dead center would be located right here. Okay, so it matches with top dead center. This is a volume of 0 and a pressure of 0. So we can see that we can have our piston top lined up with our volume of 0. So if the piston, our cylinder top to be at 0. So if our piston were to move all the way to the top right here, it would essentially read a volume of 0. Now, we already know that a piston cannot reach a volume of 0 because it actually has to move between bottom dead center and top dead center, and there has to be a volume of clearance. So this is essentially your volume of clearance, and your volume displaced is actually between top dead center and bottom dead center. So we can draw, and sorry about that, so we can actually draw that if we had the piston at bottom dead center, then this would be our boundary for our piston. So our piston is going to be moving between top dead center and bottom dead center. It's going to be moving up and down. And as such, this volume here is called VD. So the distance between here and here on the graph is actually the volume displaced. And then VC is the volume displaced by this movement right here. Now, we don't actually move into VC, so that's why the PV diagram never reaches our left side. So we can see that our left side here is kind of hidden from, it doesn't have any line movement through it. And then below bottom dead center either, because we don't ever reach that level with the piston. The piston moves between bottom dead center and top dead center. And so now we can start understanding what is happening in the engine and what's going on. So we can choose a starting point anywhere we want on the cycle because it is a cycle. And the point we're going to choose to start with is our intake valve closing. So typically we start with our intake valve closing. And we can label the intake valve closing as IVC. Okay, so we're going to label the intake valve closing as IVC. And we're going to see that our IVC is going to happen at this point right here. So we're going to label this point as IVC. And we're going to label it as point 1. We're going to write IVC, and we're going to talk about it a little bit. So IVC stands for intake valve closing. And typically at bottom dead center, so whenever your piston is all the way at the bottom, you typically close your intake valve. Okay, that means that you went from top dead center before. So you went from this point right here before, okay, and you moved along this arrow right here, and you moved to bottom dead center. And during that time, you were intaking some air. So your intake valve was open, and you were increasing the volume of your piston. So your piston was moving from top to bottom. And by doing so, you're filling your cylinder with air and fuel. Okay, and at point 1, once we're done with filling up at bottom dead center, we're going to close our intake valve. Now, in real life, we don't close our intake valve necessarily exactly at point 1. It can be a little bit before, a little bit after, but that's the idea. Then what we're going to do is we're going to close the intake valve, and we're going to continue from this point and move up the diagram with this arrow right here. And we're going to compress our air and fuel. So our air and fuel is now locked into the cylinder and is compressing. We're going from bottom dead center to top dead center, and we're compressing. And when we get close to top dead center, what we have is we actually have our ignition. Okay, so our ignition occurs at point 2. We can call this point 2. And we have our ignition that happens. So what happens there is our piston cylinder assembly is going to be compressed enough and pressured enough that we can usually spark the gasoline and start igniting and start our combustion. And then our combustion phase is going to basically occur from point 2 all the way to point 3, and a little bit more too down this way. So from point 2 to point 3, we're increasing the pressure. So the pressure is increasing a lot between point 2 and point 3 to reach a maximum point. Now, what we're going to do in a later video is we're going to go through this PV diagram again and kind of explain what is happening and draw it by ourselves. So without drawing this one, we're going to do an example problem where we can actually draw the PV diagram fully ourselves instead of having one that's already drawn, and we'll explain a little bit more about everything and all the steps. Then from point 3, we see that we've reached top dead center. So now our piston cylinder assembly, if you look at the bottom, is going to move down again. And by moving down, we're going to be expanding. So this is called expansion. And in the expansion phase, what we're doing is we're lowering the pressure by increasing the volume. And then our exhaust opens at point 4. So we can call this point 4. Our exhaust opens. And what opening our exhaust does is it allows us to release the exhaust gases. And as we release the exhaust gases, our pressure goes down even more. Okay, and we can see that our pressure drops pretty drastically. We have a 0.5 here that we're going to call the point at bottom dead center. And our exhaust is still open. And so we can write this value, this number 4, we can write as EVO sometimes. Okay, so instead of writing exhaust opens, we write EVO. So I'll write EVO next on our list of things that are going to happen. Then the next thing that's going to happen after EVO is we're going to go back to top dead center. And by going back to top dead center, we're going to get rid of all these exhaust gases. So if you go back to an earlier video, we kind of explained the 4-stroke cycle. You can go back to the 4-stroke cycle and kind of see what's happening. But essentially, our piston is moving from bottom to top, and we're getting rid of all our exhaust gases. Once we reach 0.6, which is going to be labeled right here at this last point, our 0.6 is going to be where the following happens. We're going to have our exhaust valve closing, called EVC, and our intake valve opening. Okay, so we're going to write EVC and IVO. So as the piston reaches top dead center, we now close the exhaust valve because we've gotten rid of most of the exhaust gases. And now we're going to open our intake valve to then let the air in back to point 1. And we're going to go back to point 1 by going back to bottom dead center. So that's basically how a cycle would look like in terms of pressure around the whole system. And we can see that the pressure increases a lot during combustion, and that is a good thing because that means we have more work done. Okay, so we can actually, following that, what we can say is that our work total is going to be equal to the following. So we can find what our work total would be. And what we can do is we can basically say, okay, work total is equal to work from 1 to 2 plus work from 2 to 3 plus work from 3 to 4 plus work from 4 to 5 plus work from 5 to 6 plus work from 6 to 1. We're basically going around the PV diagram and we're plotting the whole work throughout this PV diagram. And the idea here is that we can solve for the work. And we know that the work is the integral of PDV. Now, the nice thing about the integral of PDV is that it is actually, on this diagram, it is shown, or it is, you can kind of figure it out from the area under the curve. The definition of an integral is the area under the curve. So that means that if we can find the area under the curve for this diagram for each curve, so curve 1 to 2, curve 2 to 3, so we've pieced it up into different pieces, we can actually find the total work. Okay? And so we'll look at, in future videos, we'll look at some equations that we can use to be able to find the total work. Okay. So one more, so that's about it here. Now, this would allow us to find the work inside your combustion chamber. And this is not necessarily the work that goes out to your tires or the work that goes out to your wheels if your engine is mounted in a car, but it is the work that is directly coming out of the pressure within your system. All the losses due to friction are not taken into account at this point. At this point, we're just looking at the pressure inside our engine and how much work that pressure would create if everything was frictionless. So then we'll have to look at how that work evolves if we start to include friction. So the name of the work without friction and inside the combustion chamber is called indicated work, because indicated work was actually called indicated because these plots of PV diagrams used to be called indicators. So they just decided to call it indicated work. Now, what we're going to look at in the next video is what brake work is. And essentially, brake work will take into account the loss to friction, and it will be the work at the output of the engine rather than just the theoretical work that is created by the pressure inside the engine. So we'll see you in the next video to talk about brake work. Thank you for watching, and please subscribe if you're interested in these videos. Thank you.